In this video, we proceed to page 17, where we will talk about the complement of an event. You see, the complement of an event represents the set of all outcomes from the sample space that are not in the original event. In other words, if our interest is event A, then the complement of event A will be denoted as A prime or A with a superscript C, and it represents all outcomes that do not satisfy event A itself. You can think of it as the opposite scenario, so that if A is the event that an even number turns up when you throw a die, the complement of that event will be all outcomes that are not in event A, namely odd numbers. So let's take an example to drive this home even further. Suppose you roll two dice, and one of the dice is red with faces 1 to 6, as we can see here on the screen, and the other one is green with faces 1 to 6. The requirement of this problem is to find the probability of the event that the sum is at least 3. So whenever we throw this die, what we're observing is the sum that comes up. And when the sum comes up, we're interested in all instances where the sum is at least 3 or more. So as it stands, we can define the event A as the event of obtaining a sum that is either equal to 3, at least 3, or greater than 3. Okay? So to determine the probability of this event, probability of A, we're interested in the number of points in the sample space that satisfy event A all over number of points in the sample space. Well, as far as sums are concerned, if the red die throws a 1 and the green die shows a 1, 1 plus 1 will be 2. If it is 1 and 2, the sum will be 3. 1 and 3, the sum will be 4, and so on. So our interest is all of these numbers here in the cells. These are the possible sums. Well, our interest then will be to look at all instances where the sum is at least 3, that is equal to 3 or more. That would be all of this bunch. So that would be all of this bunch that I am highlighting in purple. And the number of that is 35 out of 36. On the other hand, if we are to determine the probability of the complement, that would be the probability of A prime, or probability of A, let me write that, of A prime, or probability of A complement. That is the probability that the sum is not greater than or equal to 3. In other words, the sum is only what? That of 2. So that will be number of points in A complement all over number of points in the sample space. That will be 1 out of 36. Well, what do we notice? The probability of A, of an event, was 35 over 36 in this example, plus the probability of its complement. That gives us 36 over 36, which is equal to 1. So this principle this observation here provides a basis for the relationship between the probability of an event A and the probability of its complement. Why is this simple principle, why is it very important to us? You see, for instance, if I were to tell you that a coin is tossed 3 times and you are to find the probability that that at least one tail shows up in the toss of the coin. A very, very notable fact is in tossing the 3 coins, in tossing the coin 3 times, we are looking at the fact that you either get no tail or at least one tail. So it's either you get no tail or at least one tail shows up. If we're considering probabilities, it is such that the probability of no tail, none of tails, plus probability of at least one tail, this is equal to the probability of certainty, which is 1. In English, you will read this as probability, that 1 represents certainty, the probability of certainty. So it is certain that when you toss this coin 3 times, you will either get no tail or at least one tail. And these two events are mutually exclusive. So this can be a very useful formula when we're computing probabilities, especially if the number of times a coin is tossed is a considerably large number. Considering or finding the probability of no tail, which might be easier to find, can be subtracted from 1 in order to get this final probability. In this way, we find this formula or this relationship between the probability of an event and its complement to be very useful. With that said, let's go on to independent events. You'll recall that in two events or processes are independent if the occurrence of one particularly has no bearing on the occurrence of the other one. So if I flip two coins, the outcome on one coin is independent of the outcome on the other coin. Or if I flip a coin and roll a die, the outcome on those two items or those two items are definitely independent of each other. How do we compute probabilities for independent events? We use the multiplication rule. In other words, if we observe that A and B are independent events, then, and we're told to find the probability of both A and B, in that case, we'll need to take the probability of A separately, independently, the probability of B separately, and multiply them. Let's put this to use or exemplify the use of this formula in this example. Consider rolling two dice. If 1/6 of the time the first die is a 1, this means that the probability of 1 whenever we roll one of the dice is 1/6. And 1/6 of those times, the second die is also a 1, which means on the second die, probability of a 1 is also 1/6. The question before us is, if we actually roll these two dice, what is the chance or the probability of getting two ones? Probability of getting two ones will be the probability of 1 on first die and 1 on second die. In this case, we have two events, in which case we are looking at the event that 1 shows up on the first die and the event that 1 also shows up on the second die. We might reckon that for both events, these events are independent. What you get on the first die does not dictate what you get on the second die. So they are independent events. Because they are independent, we can use the multiplication rule for finding this probability. So we look at probability of 1 on first die, which according to the question is equal to 1/6, multiplied by probability of 1 on the second die, which according to the question is also another 1/6. Multiply them together. 1 times 1 is 1, and 6 multiplied by 6 is 36. All right. Here's another extension of the problem. What if there was another blue die independent of the other two? What is the probability of rolling 3 dice and getting all ones? Well, if we're rolling 3 dice, the outcome on each of those dice follows pretty much the same principle as when you have 2 dice. So probability of getting all ones would be probability of 1 on first die multiplied by probability of 1 on the second die, and lastly probability of 1 on the blue die too, which will be 1/6 1 over 6, 1 over 6, all multiplied together to get a result of 1 out of 216. To proceed, let's see another example on page 19. In airline applications, failure of a component can result in a catastrophe. As a result, many airline components utilize something called triple modular redundancy. This means that a critical component has two backup components that may be utilized should the initial component fail. Suppose a certain critical airline component has a probability failure of 0.0064 and the system that utilizes the component is part of a triple modular redundancy. Assuming that each component's failure or success is independent of the others, what is the probability that all three components fail, resulting in a disaster for the flight? Well, probability for a single component, probability of failure on a single component is 0.0064. Keeping this assumption in mind that the failure or success of one component is independent of the other, we approach the question that the probability that all three components fail as follows. This will be interpreted as probability as what the first fails and the second one also fails and the third one also what fails. Well, since components are independent, it means we can use the multiplication rule for independent events, which indicates that we can take the probability that the first one fails and becomes multiplied, probability that the second one fails and becomes multiplied, probability that the third one fails. That will be for each of them, based on independence, we use the provided probability for each component. So this times 0.064 multiplied by 0.064, and that would be equal to about 7 zeros. 1, 1, 2, 3, 4, 5, 6. And then you have 2, 6, 1, 4, 4. This is a very, very unusual probability, which is good in the construction of what? Airlines. This represents a very rare event that all three would what? Would fail.